Okay, so let's talk about this idea of two-force and three-force bodies. This is really an extension of our equilibrium in 2D. But the special case, if I only have two forces on an object. So if I look at this little bracket here, or this elbow, I have two forces. And the thing is, if we were to try and solve for those two forces, and we were to say, let's take our sum of the forces in the y direction, set it equal to 0, well, this is not possible. And the reason it's not possible is because both of them have a positive y component. So this is not, it cannot be in equilibrium. And in fact, what we find out is the only way that a two-force member can be in equilibrium is if these forces are in line with each other and equal and opposite. We can write this statement. So we can say that in order for this two-force body to be in equilibrium, it has to have the same line of action, equal in magnitude, and opposite in direction. So the only two options are either as I have it shown there, or with the two forces pointing towards each other. So not really exciting, not too much we can do with that. Um, the big question is, what about if there are three forces or a three-force body? Let me give myself a little more room here. And for a three-force body, so if I have a three-force body that looks like this, what we can actually prove or show is that if I were to trace back these lines, those no longer have to be the same, but wherever those two intersect, the third one is also going to reach. So there's this concurrent line of action between all three forces. So basically, that all these three forces must intersect at a single point to be concurrent and in order to be in static equilibrium. Why do we care? Because this will allow us to solve problems graphically. And the way that works is because I can move vectors around. In this case, I have, if I called this F1, F2, and F3, I have this F1, and then I have F2, and let me draw this in a different place. And I'm going to add these head to tail, F2, and then I would have F3. And it ends up, although I didn't do a very good job here, it ends up forming a triangle, and then you can use all sorts of geometry and trigonometry in order to solve these things. I think it's a much harder method, but I'll give you one example. I'm not a big fan. I think you're better off just sticking with our sum of the forces x, sum of the forces y. But let's look at an example of how we would do it with this new method and compare it to the old method. So for this example, we have this elbow shape. We have 320 Newton force we're supporting. We want to find our reactions at point A and B. A is a roller, B is a point force. So if I were to look at my free body diagram for what's going on here, what I have is the 300 Newton force. Now at the roller at A, I know that I have a reaction A, and it has to be in this one direction because it's a roller, right? So that intersects at this point. That means at B, B would have an X and a Y component. Well, I know that it must be concurrent along here, and I also have a reaction at B that looks like that. So with that in mind, I could add these head to tail, and with this I'm going to say I'm going to have this B, I'm going to add to that 320, sorry, 300. No, 320. I miswrote it here, didn't I? This would be 320. Going down, and then the reaction at A being horizontal. So I end up with actually a right triangle, which makes life a little bit easier. Usually when you're using this method, they aren't quite as easy. And I can solve for some angles. I might want to solve for this interior angle beta. Actually, let's do this alpha because I already have a B up there. Let me erase that and put in a, let's do theta. Theta is always a good one. So with theta, I know that that angle has to be along the same line of action, meaning I know what this height is, and this height would be 80, and this distance over would have to be 150. So I could find this little angle theta in there, and I found that to be 28.1 degrees. And with that 28.1, I could find out what these values are because I know that the tangent of that angle is equal to the opposite over adjacent. And from that, I end up with A being, what, 600 newtons. And like I said, this one's a little bit easier. Normally you have to use a lot of sines, a lot of cosines, because it's rarely that it is a right triangle. And from here, then I could also use the sine of that angle is equal to the opposite over the hypotenuse, or B is 680 newtons, and I know that the angle of that vector is 28.1 degrees from that positive x. So that's our new way of finding it. To verify it, let's check this with our old way and what I'm calling my preferred way, because this way, this new way, only works with 3 vectors. But with the old way, we end up with a free body diagram. Notice I'm leaving the bx and by as horizontal and vertical instead of actually finding the angle. And with this way, I would sum the moments about a point that make 2 forces go away. In this case, it's point B. So let's see, I'd have that A and its lever arm minus a 320 and its lever arm equal to 0. So I found a reaction at A equal to 600 newtons. Same thing I got up there, hopefully. Yep. And from sum of the forces in the x direction equals 0, I know that Bx must be equal to 600 newtons going the opposite direction. I didn't really draw my direction in there for the first one, but something like that. Maybe I could call it negative if I wanted. Probably should show something on there though. And from sum of the forces in the y direction equals 0, I know that By is equal to this 320 newtons up. So to compare what I just did a second ago, then my total reaction at B, square root of 600 squared plus this 320 squared will give me 680 newtons. And if I did the inverse tangent, I would find out that that's at an angle of 28.1 degrees. So we can show it either way, but that's 2 3/4 bodies. Use them if you want. For the homework, you can do them either way. For exams, you can do it either way. Doesn't much matter to me. I'll grade them one way or the others. Hope that was helpful. I'll talk to you all later. Bye.